All right, good morning, folks. We're going to get started with the vendor session and start off with Deepak talking about OpenMP in the Cray compiling environment from Hewlett Packard Enterprise.
Thank you. So good morning, everyone. So I'll talk about OpenMP in Cray compiling environment, or CCE. So I'll start with just an overview of CCE. So when I talk about CCE, really I'm talking about two compilers. There's our Fortran compiler, which is based on what we call our classic Cray compiler. So this is a compiler infrastructure that we've been developing in-house for really decades. So it's very mature. And this is what we use for our Fortran compilation. It supports the latest Fortran standards, including the latest parallel language features in Fortran. It's a proprietary front end, proprietary optimizer. It has support for a lot of advanced fine-grained optimizations, vectorization, auto-parallelization, and of course, OpenMP, as well as other models for targeting accelerators, OpenACC. And then it uses LLVM as a backend. So that's what we use for Fortran. For C and C++, in the last several years, we moved towards using Clang. And so we're Clang-based for C and C++. We've added enhancements to our Clang implementation to provide capabilities that we had in our prior iteration of our C and C++ compilers. So support for unified parallel C, for example, was added. And then we also added a number of other enhancements, improving support for vectorization and other optimizations. And we also have some alternate code paths that we take when we're generating code for GPUs in our Clang implementation. We support, for offloading, we support a variety of models. So OpenMP is the model that we support for both NVIDIA and AMD GPUs. And it's supported both in our C, C++, and Fortran compilers. So that's the most widely supported model that we have for accelerators. For our Fortran compiler, we also support OpenACC, and we're working towards providing full support for OpenACC in the 2023 timeframe for Fortran. And then for AMD GPUs, we also provide support for HIP in our Clang compiler. So in terms of the different types of target architectures we support, of course, we support NVIDIA GPUs and AMD GPUs. We support various flavors of CPUs, x86-based, Intel and AMD-based, and ARM-based. And we have different systems that we sell with various configurations of those. CCE also supports integration with program development tools. So we have our perf tool suite, which provides performance analysis. And then this can be used both to visualize performance data. It can also provide feedback to users to help guide tuning of their applications, including parallelizing their applications. So we have a tool that we call Reveal, or the Code Parallelization Assistant, which specifically for OpenMP can take performance data and combine that with static analysis of your whole program and provide guidance on how to use OpenMP to parallelize your code. So moving on. I agree. I don't know why they decided to do that. All right, so this diagram just kind of shows the different components of the compiler that I mentioned. So again, there's two different paths for Fortran and C, C++. Our Fortran compiler has a number of proprietary components to it. As you'll see in the diagram, we do have a Cray PTX code generator for NVIDIA targets. That's still sort of our in-house developed code gen. That's something that we're considering moving to LLVM for that as well, but we haven't made that transition yet. For other targets, we do use LLVM as our code gen for our Fortran compiler. And then again, for our C and C++, we use Clang, but we do have a number of enhancements that we've added to Clang. And we also, with our compiler, it comes coupled with a number of proprietary libraries for math, for doing mem copies and mem sets. And we will actually do pattern matching in our Fortran compiler to leverage some of those libraries when we see we can do so. We have our OpenMP runtimes, so libcraymp, libcrayacc. Libcrayacc is actually a general offloading library that supports both OpenMP as well as OpenACC. It was initially designed, in fact, for OpenACC, but we enhanced it to be able to be used for OpenMP. And then we have other libraries that come coupled with CCE as well. Okay, so optimized execution with CCE is a big focus for us. We have general compiler optimization capabilities across the languages. So vectorization, partial vectorization due to incomplete hardware support is also there. Loop unrolling, loop distribution, making automatic use of FMAs, and also support for like gather scatter instructions, vectorization of non-stride one loads and stores. That's available. For Fortran, we do have more advanced vectorization capabilities. So support for outer and arbitrary loop vectorization. We have a number of loop transformations that are available in our Fortran compiler, automatic loop transformations that we can do, interchange, peeling, collapse, fusion, fission, etc. We also support automatic multi-threading, which will leverage the infrastructure we have for OpenMP. So we can analyze loops, and if we determine that it's both profitable and legal, we can auto-thread loops. And there's, as I had mentioned earlier, there's also a lot of fine-grained optimization control available in our Fortran compiler. And then coupled with our compiler, we have a number of the optimized libraries, which I mentioned previously. One note here for the optimized OpenMP, OpenACC runtime library support. We actually added a layer on that, which is compatible with the code that's generated from LLVM for OpenMP. And so that enables us to generate interoperability with other Clang-based compilers that are compiling OpenMP codes. So you can, in your application, you might have some files which are compiled with upstream Clang, for example, and other files which are compiled with Cray compiler. And we have the ability to link those together and still it'll work. So this is just a slide just saying a little bit about HIP support. So this is AMD provided language for targeting AMD GPUs. So we've been supporting this in CCE via our Clang compiler since 2020. We really just leverage the AMD's open source HIP implementation, which they made available in Clang. And we rely on the ROCm installation for HIP header files and the runtime libraries. So that's we provide support for HIP, but we rely on a ROCm installation. You need to point to the ROCm installation headers to use it with CCE. AMD also provides a HIP CC wrapper, which will add some additional options. So CCE doesn't add those additional compiler options automatically when compiling HIP. That's something we're considering doing in a future release, adding additional optimizations automatically when using our CCE PE driver to better optimize HIP codes. But right now you have to add those additional options. And just the slide just provides a little extra information or where to go if you want further documentation on CCE and the different flavors of CCE that we have. And then if you're on an HP system, these are the man pages that you can look at just to get general information about our compiler and OpenMP specific information. Okay, so let's go into the OpenMP support. So we support CPU threading and vectorization for a number of different CPUs, x86 and ARM-based CPUs. As I had mentioned earlier, we support GPU offloading both for NVIDIA and AMD GPU targets. And we have our proprietary OpenMP runtime libraries. As I had mentioned earlier, there is cross-language, cross-vendor interoperability support. So again, you can use different compilers. You can and you can link them together with our Cray OpenMP runtime, and that should work. We also have our optimized code generation path for offload regions that we use both for our Fortran compiler as well as our Clang compiler. So we have our own code gen for that. And in terms of 5.0 support, 5.x support, so that's in progress. 5.0 is mostly done. And we have been implementing that support over the past several releases. We're working towards completing 5.2 by next year. So that's our goal. And in terms of flags, you can use, there's just the standard FOpenMP flags that Clang uses for C and C++. And for Fortran, we also support the same flag. There's also our older legacy option, HOMP, that you can use to enable OpenMP. And then as Clang has the ability to enable or disable OpenMP SIMD functionality specifically. I don't believe that's in our Fortran compiler yet, but that's something we're adding very soon. So that might make it into CC15, actually, the ability to specifically compile for SIMD functionality, since that seems to be often requested. When you're using our programming environment, we also have modules that you can load as a convenience for when you're targeting different GPU targets. And when you load those modules, you can just compile your code with FOpenMP. You don't have to add all the additional flags to it in order to target a specific GPU architecture. The driver will automatically take care of adding the necessary options for that when you load those targeting modules. All right, so this just lists all of the various 5.0 features that we added support for over the last several releases. As you can see, 5.0 was a huge addition to the specification. So it's been quite a lot of work to try to get all of that in. We still have some remaining features that we're working on completing. As you can see, some of the capabilities were made available in our C and C++ compiler. Some are made available in our Fortran compiler. So they don't necessarily always come together because they are two different compilers ultimately. And so, for example, loop construct, we do have support for that for a Fortran compiler. We're still working on finishing support for that for our C and C++ compiler. Mappers is an example where we have support in place in our Clang compiler, but not yet for Fortran. And as you can see, there's other features there where there might be lacking implementation for one language or the other. And when you look at our man page and you look at the intro OpenMP man page specifically, it will list the features that aren't yet supported. So you can see that. And there's also an additional list of limitations that we document. If there's particular capabilities that are supported, but there might be certain things that aren't quite working or might be limited in some way, we'll document that as well. Areas of OpenMP and affinity control. So the way we handle that is we support a hierarchical affinity handling, essentially. So your workload manager, it will assign an affinity mask to each of the ranks. And then OpenMP affinity control can be used to essentially create place partitions within that affinity mask. With CCE, the CPU numbering is interpreted relative to cores visible to the rank. And I think different implementations might handle that differently, where they kind of do it an absolute numbering for the entire device, but we interpret them relative to within the rank. So because of that, and because of those differences, we generally would recommend using the symbolic place names for places like sockets, cores, threads, etc. That's available in OpenMP. In terms of a default procbind policy, I think this might have come up yesterday, actually. So we have a policy that we call auto, which isn't exactly one of any of the policies that are defined in the specification. It's what we think is generally the sensible thing to do based on the affinity mask setting from the workload manager. It'll partition the place list, and threads will bind to places within the partition. But it does allow for threads to migrate within the partition. So it's not necessarily bound to a specific place in the partition, but it's bound to a set of places within a partition. That's how that works. If you do procbind equals true, then that will map directly to spread. It's just an alias for spread in our implementation. Okay, a few notes on SIMD support. So SIMD is very useful for providing additional vectorization safety information, similar to IVDEP. And our optimizer will employ standard loop dependence analysis to do automatic vectorization. Particular for our Fortran compiler, it's fairly advanced, I would say, in that respect, and fairly mature. We will, if we see a SIMD construct, we will honor the semantics. So any private clause, reduction clause, linear, etc., those will all be handled correctly. Whether we actually vectorize according to the SIMD construct will depend both on what's provided on the SIMD directive as well as analysis that we do. So in some cases, if we determine that it's not profitable to vectorize, we won't vectorize it. We might see that for whatever reason, that particular loop cannot be vectorized properly on the target architecture, in which case we won't vectorize in that case, but we will still generate functionally correct code for it. There is a directive that we make available for our Fortran compiler, prefer vector. And so if you do want to sort of override that compiler profitability analysis, you can use that, and then we will, it's kind of a more prescriptive knob to just do the vectorization. For declare SIMD functions, we support it kind of. So if the function can be inlined, then we'll inline it, and then we'll do the vectorization just through our normal vectorization pass. But if we're not able to inline the function, we don't generate vector versions of them. So, and if a declare SIMD function is called, which we weren't able to inline, and it's in a SIMD construct, then we will either just execute that portion of it serially, or we might end up just not vectorizing the loop. And as I had mentioned, we do have a separate control for enabling OpenMP SIMD functionality. And again, I think that we will also be adding that very soon to our Fortran compiler. All right, so this slide just kind of gives an overview of how we handle offloading to the GPU and how those map. So the table here shows for both NVIDIA and AMD GPUs what our mapping strategy is for OpenMP, and it also just as a reference shows it for OpenACC for Fortran as well. So as you may know, for OpenACC, it has these three levels: gang, worker, vector, and those kind of map directly at a thread block, warp, thread, or work group, wavefront, work item for AMD. For our OpenMP implementation for Fortran, we kind of support two levels. So teams will do what you would expect. It will map to thread blocks or work groups. For threads within a thread block, the way to control that within our Fortran implementation is to use the SIMD directive. A lot of the features that are in parallel, I think when we were initially designing this, we felt didn't map very well to the GPU, and so we'll kind of default to running parallel with one thread, but we will use SIMD to be able to take advantage of all the threads in the thread block where possible. Of course, if you do just specify on a loop like teams distribute parallel for or parallel do, it doesn't mean you're not going to actually leverage all the threads in your thread block. As I had mentioned for our Fortran compiler, we do very aggressive analysis to see if loops are capable of being parallelized, and in that case, we will take full advantage of all the threads if we see that it's legal to do so. For our Clang compiler, we do support both generating multi-threading for parallel and SIMD for parallel in more cases. There are certain things that if you add in your parallel regions, it might end up executing those with a single thread. And so there are some limitations there, which we document. But we do intend to generate parallel code more often for parallel for our Clang implementation. And both of these things are things that we've been having discussions on improving, being able to support all three levels of parallelism in a way that's more natural to users. So we realize that it's not ideal that our mapping strategy doesn't match what other compilers might do. For users, that's not very helpful. So we're trying to get to a place where we're just going to do the thing that makes sense for users. When they express their parallelism, we'll map it and try to take full advantage of the GPU, and also do it in a way that is compatible with what other compilers are doing. All right. So we provide some support when you're using offloading, some additional runtime messaging that's optionally available with a Cray ACC debug option with different levels of verbosity. And it provides a lot of useful information for documenting the offloading activity with a line number information. It'll give you information about allocates, frees, transfers, kernel launches, information specific about your kernel. And we also add information in there about pointer attachment. If it's using unified memory, if it's able to utilize unified memory, there'll be information in there about that as well. This is a really useful debugging tool. Asynchronous support. So we've been supporting asynchronous offload with OpenMP in a fairly optimized way for quite a while. We will map no-wait constructs to independent GPU streams. So if you just say like target no-wait and you don't have any dependencies on there, we will map them to independent GPU streams so you can get concurrency that way. With depend clauses, we will map those to different streams, and we have logic to do that. And so if you have your bunch of different device constructs with depend clauses, we will generate, we'll enqueue operations to the streams. We'll add the necessary wait operations into the streams to join the various operations and get the ordering that you would expect. So that works really well. We also added detached task support recently. Well, not recently, in 2020. So that's in place. And that tends to be useful also when you're dealing with OpenMP and trying to coordinate that with device operations. That facility is useful. There are some limitations, I should say, with how we handle the no-wait constructs. When you're dealing with trying to do dependencies between host tasks and target tasks, essentially, that you're offloading to the device. Because in our model, we don't actually generate target tasks per se in our runtime. We're not leveraging the infrastructure for handling task dependencies for host tasks. We're not leveraging that for device tasks. We're using a different method for managing that. And so currently, if you have host tasks and you have GPU tasks and there's dependencies between them, we're going to be adding overly conservative synchronization there. Our rationale on this was that we haven't up to this point put a lot of effort on improving that, because we just don't typically tend to see host tasks plus GPU device tasks used together very often. And so we thought that this wasn't as much of a priority for users. But we have been considering different ways in which we can improve on that. One would be to leverage a similar model that like LVM is using with the hidden helper threads. That might actually be much more viable for us if we're going to be supporting that anyway with the upcoming free agent task capability, which is a way of kind of adding helper threads as part of the specification in a sense. So that we might use that to better support this. And there's other schemes we can use to even avoid the use of helper threads to better handle these sort of cases that we're considering. We also added some last year. We added some better support for multi-threaded use of the GPU. Relaxed locking strategy compared to what we were doing earlier. So we're getting better concurrency now when you have multiple threads that are trying to interact with the GPU through our runtime. All right, so this table summarizes some of the memory management capabilities that we have in place. So we can use the pinned trait with allocators to essentially map that to malloc host or hip malloc host, where you can essentially allocate pin memory that's accessible from the NVIDIA or the AMD GPU. So that's one type of allocator that users can use. Another is we have the C group memalloc predefined allocator that we support. So you can use that if you want to explicitly allocate private variables on a Teams construct in shared memory, you can specify that in an allocate clause, and we will allocate those in that GPU shared memory using that allocator. And then there's also an extension for returning a special memory allocator for allocating managed memory. And we'll just map that when you use that particular allocator, we'll map that to a call to CUDA malloc managed or hit malloc managed, depending on the GPU target. The other thing that we have is an environment variable, use unified memory. And so this is an environment variable that you can set that will tell the runtime to leverage pinned memory or managed memory to avoid doing allocations and transfers on map operations. And so you can set that, and it will do in-place accesses in pinned memory, or if you have managed memory, it'll take advantage of that. And again, using the Cray ACC debug messaging, it'll provide that information to you that it was able to leverage unified memory in those cases, rather than doing those extra allocations or data transfers. A little bit more information on the unified shared memory support, specifically for AMD GPUs. So again, as I mentioned, we have the Cray ACC use unified memory option, which can be used for enabling the managed memory for map clauses. And then that, if you have that set, it'll skip the explicit allocate and transfers. The other thing you can do is if you set that environment variable and also set HSA XNAC, you can also skip the allocate transfers for system memory as well. So you get sort of a dynamic setting that you can use to just use to avoid maps doing those extra allocations and transfers. With that setting for declare target like global variables, you'll still have separate device copies in that case, because that's something that the compiler is generating. If you can compile your code using the requires unified shared memory, and then that will just use pure shared memory as well. So you do that, and then you also set your HSA XNAC equals 1, and then you get a full shared memory operation in that case. All right, so this diagram is just illustrating how compiler interoperability works with CCE. So as I had mentioned earlier, you can have different source files that are some compiled with CCE, some compiled with, say, the LLVM compiler or the AMD compiler. And we have as part of when you're compiling with CCE, there's when you're linking with CCE, it'll invoke this offload linker tool. We call it Cray OpenMP offload linker, cool tool. And it will unbundle the objects, and it will create the device images. And then again, we use libcrayMP, libcrayACC as our OpenMP runtimes. And code that's generated by LLVM compiler, it can still use our runtime. So that works. One thing to keep note here, though, is that they are treated as separate device images. So you can't, for example, have device code that's generated from CCE calling into device code generated from another compiler or vice versa. We don't support that level of interaction. But as long as they're sort of self-contained in the calls that they're making, that will work in your application. All right. So next, I wanted to talk a little bit about some of the tool support we have in place for OpenMP. For profiling support, so something we've been supporting for quite a while is we have our own compiler instrumentation for OpenMP that will collect OpenMP specific data using HPE's perf tools. And whenever you load the perf tools module on a Cray system and you compile your code with our compiler, it'll automatically add this instrumentation for you. And when you run it, you can get the performance data, and then you can visualize it, and you'll see OpenMP specific regions in there. And then depending on the type of experiment you're running, you can also see accelerator specific regions in there as well. And so that works today, and that's been working for quite a while. We've been supporting OMPT version 5.0 and CCE for a number of releases at this point, but we haven't been supporting that in perf tools until recently. So the recent version of perf tools in September is supporting OMPT for the CPU, and our December release, we're planning on supporting OMPT in our perf tools for the devices as well. And so our plan is to eventually transition away from our existing compiler instrumentation approach to using OMPT for profiling. More recently, we've added some additional support, OMPT support for some additional synchronization constructs, which aren't strictly mandatory in the specification, but those are useful for enabling tools like data race detection tools like Archer. So tracking critical constructs, locks, task dependencies. We added support for that so that you can do useful data race detection for codes that are using those sorts of constructs. We're looking towards in probably next year better supporting for external monitoring interfaces that's available in 5.1. So we're going to be adding support for that. And also we're in progress is device tracing support as well. So our current OMPT implementation doesn't generate device trace records. There is an interface in OMPT to support that. We're just using the callback API right now. But we are working towards adding device trace record support for host-initiated events. So any sort of kernel submits data operations will generate trace records that the tool can see, and it'll have timestamps for when those operations were initiated and when they completed. So that will provide much better information for asynchronous execution of device constructs by leveraging the device tracing support. All right, so this slide here is just kind of showing different capabilities that's available with the OMPD support that's in CCE. So this is also something we've been supporting for a number of releases. And I would say, the three main capabilities that OMPD provides for debugging your application is enhanced backtraces. So as you can see here on the lower left, you get filtered backtraces that filter away basically runtime frames in your call stack when you're looking at it. So you can just focus on user code when you're looking at your backtraces. So that aids in debuggability. You also get information about parallel regions. So this is just showing one level of parallel regions, but if you have potentially multiple nested levels of parallel regions, you can see that through OMPD. And then also the ability to inspect ICV. So not just user variables, but if you want to look at OpenMP specific variables in the runtime, there's the ability to do that through OMPD. Of course, all of this depends on a debugger that also supports OMPD. These particular snapshots were shown using the a GDB plugin that's available on GitHub that we use to get this. LLVM is working towards adding that GDB plugin support, upstreaming it, so that will be available in LLVM. If you have that installed, you can use that. You can use that with your debugger, and then any OMPD supporting compiler, you would be able to look at information like this with it. We're also looking at adding that GDB plugin specifically for GDB for HPC, our debugger tool that we release, making that available as part of our CPE release, so that this will just sort of work out of the box for users. So this here shows recent enhancement we've made to the Reveal tool. Before with Reveal, you had the ability to look at scoping information, what variables should be privatized, what variables should be shared, what type of privatization, should it be first private, last private, that sort of thing. And then also which loops should be threaded. With the recent version of Reveal, it actually provides device construct specific help. So it'll use performance data to identify loops that it would be profitable to send to the GPU, and it will generate device constructs for those loops. And it'll also provide guidance on how to map your data It'll provide map clauses as well on those directives. And then it'll also take care of providing declare target directives for any global variables or routines that are called within those regions. So it provides that level of assistance. Now, it's true that if you just rely on this, you're not necessarily going to get the best performance, because generally what you want to do is you want to use data regions, which requires an analysis that is beyond what we currently make available. But as a first step to getting your code and getting it on a GPU, this can be very helpful for that. And then further additional iterating on that code to tune it would then be necessary. All right, so that gave an overview of the tool support. So in closing, so the CCE, it's a key component in our wider integrated Cray programming environment. So I mentioned some of the other the other pieces of that programming environment with the tools discussion, perf tools, debuggers. There's sanitizer support. Of course, the reveal tool is another part of that programming environment. There's a lot of optimized libraries that come with that programming environment. And CCE is a key component of that programming environment. It uses a Cray customized Clang/LLVM for C++ compilation. And then we have our own developed Fortran compiler and our own runtime libraries that we use for OpenMP. We focus a lot with our OpenMP implementation on tuning it for the important HPC workloads. So we don't necessarily always provide the most general support for all sorts of codes, but we try to provide at least functional support, but really focus on performance on the applications that we see as are most important for our users. And then finally, we're working towards completing 5.2 features, again, in CCE by late 2023. That's what we're planning on providing making that available. All right, so with that, thank you. And any questions?
Deepak, so when you talked about combining your CCE and LLVM upstream, and they execute separately on a device, you need two different runtimes for that. Is that correct? The LLVM,
well, so
there's specific to a feature.
Yeah, so there's the offloading runtime, which is responsible for actually doing all the host-initiated operations, or actually generating the data transfers, sending the kernel over to the device. And then once it's actually on the device and it's executing, there is a device runtime that it uses. So for code that's compiled with LLVM, it's still going to use its own device runtime. We don't touch that. But for the actual getting the code onto the device, doing the data transfers, all the mapping operations, all of that stuff, that all goes through our runtime now.
Okay, thank you.
Yep.
Sorry. Thanks for your talk. To stay with that same topic, first, LLVM, let's stick with the host for now. LLVM's host runtime is evolving, especially libomp target. I mean, libomp is fairly stable. Nobody. But libomp target is evolving. New entry points, Clang emits different code now than it did, 2 weeks ago. So you said, you're compatible to a degree where you have this wrapper layer.
Yeah.
So you're like, does it mean your next release is going to allow compatibility with the last LLVM release, or how should I imagine this?
Yeah, so there is generally potentially a lag. So the very latest, stuff that's in the development branch, not necessarily, but yes, the latest release, we will make sure that those are compatible. We test that. If there are any changes in the behavior of the entry points, we try to account for that. But that can be difficult. And we've been having those conversations about how that can create challenges for us. But yeah, we do try to maintain compatibility with the most recently released Clang.
Okay. And that brings me to the more complicated question on the device. You just said, they'll just continue using like the LLVM compiled parts will use the LLVM device runtime.
Yeah.
what if LLVM switches to, an more or less forced offload, like forced LTO model for device code, where the runtime is only added late in the linker and so on and so forth, not as part of every translation unit? How would that, is there a plan to handle that?
I'm not sure at this point. I would have to think about that, how we would handle that case.
All right.
Yeah.
So let's push on that one a little bit more, though. So I think you're aware that, at least from the standpoint of NNSA users, it would be highly desirable to be able to call into device functions that have been generated by a different compiler. So certainly, it'd be even better if we could just make them fully compatible, right?
Yeah.
Right now, I think the interoperability is typically one of, even on the host, you can't really use, mix LLVMs regions with CCE regions, kind of in the stack. If you start with an LLVM one at the top and stay with LLVM, that's good. If you start with CCE, but at least the cross calling on the device without using OpenMP seems like we ought to be able to figure out a way to make that work. And I don't know if it's something OpenMP can help with, defining some kind of ABI or something, or providing an interface by which you can get the actual symbols back or something.
Yeah, it's tricky because, we have our own way in which we generate code for kernels, which we use a kind of a different, in some cases, a different model. For example, Clang might be using like what they call generic mode, whereas we generally are very aggressive in trying to do SPIMD mode in as many cases as possible. I think Clang is moving in that direction also, but there still might be some incompatibilities in how we generate that code. And so in general, calling from our code to LLVM or vice versa, that might be tricky. So that would require closer coordination, I think, in how we're generating code to make sure that would work. Yeah, I think we might try to work towards identifying specific cases where we can provide guarantees that it would work and try to codify, these are the specific cases where this is allowed and document that. That's something we can work towards. Oh, sure. So he asked about the C group memory allocator and whether it's only available for a Fortran compiler or for Clang. I think maybe that was, let me go back here. So this particular capability, we definitely support that for Fortran only, as you said. I'm not sure what the status of that currently is in Clang, if that's supported or not. Right, yeah. And we also will do that in our Clang compiler. We'll try to automatically take advantage of shared memory. In terms of the actual use of the allocate clause on Teams constructs, I'm not sure if that's handled right now in Clang for memory allocators. That's something we specifically added for Fortran to be able to explicitly say, I want you to use this. I don't think that level of control is yet available in Clang. Okay, thank you.